to the recording in progress. So thanks to the seminar committee to organize this as short notice. So thank everybody to connect to be here. And this week we have the pleasure to have Marc visiting our group, and he kindly accepted to give us this seminar. Marc is associate professor of astrophysics at the Observatory of Paris and at the University of Paris, and is also adjunct professor at the University of California, Santa Cruz, and is currently on sabbatical leave, spending 3 years at the Instituto de Astrofísica de Canarias, ceremonial fellow, and is an expert in the formation and evolution of galaxies, and is particularly interested in the morphology of galaxy in the context of large cosmological survey, and is indeed involved in several of these major projects that will take place in the next decade, like JWST, Euclid, JPAS. And since the beginning of his career, his line of research are at the crossroad between two fields, which are astrophysics and machine learning. And is one of the pioneers in the use of machine learning in astronomy. And today, it's a pleasure to have him here. And we'd like to learn more about the impact that this machine learning will have in galaxy survey in particular in the years to come. So, Marc, if you want to add more, otherwise I leave you the stage.
Thank you very much, Luca. I hope everyone can hear me. And thank you for those who are here and also connected on Zoom. So I slightly changed the title of my talk to focus it more on what we can do or how data-driven approaches such as deep learning can be used to better understand or constrain the physics of galaxy formation. So these are efforts done within my group, although I'll try to describe a more general context. I've listed here some of my students and postdocs and also collaborators, but this is an effort of several people also, which are not listed. So since I understand this is a multidisciplinary institute, I will start by the basics. I hope this is not too long. And so basically what we're trying to understand is how galaxies form. And I said that maybe I will start by defining what's a galaxy or how we understand galaxies today. And essentially, galaxies could be seen in a modern way as overdensities of dark matter. So it's essentially, an overdensity of dark matter in some place in the universe, which contains, because of this overdensity, a small fraction of what we call baryons, which is what we observe in the center of these dark matter halos. And so what we're trying to understand is what are the physical processes that regulate this. So this is one basic view of a galaxy. If you want to even look at it in a more broad context, in fact, galaxies can be seen as the places where stars are born in our universe. So it's basically they are machines or somehow efficient or inefficient. This is what we're trying to understand, but that transform gas, which is the primordial element in the universe, which basically is hydrogen, and that is transformed in these overdensities into stars. And so what we're trying to understand when we do galaxy formation is what's happening there in these high density regions, where of course you need to couple very small scales where the actual star formation happens, where the gas collapses, to very large scales, because the gas is fed in the cosmic web, and all these halos are interconnected. And so what happens inside is, of course, nonlinear physics, complex because of the coupling of different scales. And what you're trying to understand is how this transformation between gas and stars is happening across, ideally, cosmic time. So since the first galaxies were created until today. And of course, if you try to understand these in detail, it becomes extremely complicated. And so one approach that people have tried to do in the past years is instead of going object by object, is trying to have a statistical view of how star formation and how galaxies move or evolve. And so this is what I will call the era of statistics, in which what we have been doing is gathering more and more data of galaxies, what we call objects, And instead of getting one particular object, what we try to do is observe lots of them at different cosmic epochs and establish scaling relations or correlations between different quantities to try to constrain what are the global trends that regulate star formation in the universe. And you can see here as a function of time how this is an incomplete view, but how the number of objects have been increasing with the number of galaxy samples that we have at our hands. And today, basically, we are around 1 million objects at different, so we have samples with millions or slightly below the million objects at the low and high redshifts. And this essentially comes from campaigns from the ground-based telescopes, such as Sloan, or even space, like using HST, like, for example, the Cosmos Survey. And so basically, this is equivalent to say, I don't really care of what's happening in detail in these halos. I put a kind of black box, and I say that there will be some global mechanisms that will trigger star formation, enhance star formation, others that will try to suppress star formation. And I try to establish more statistical, see objects as statistical elements, and what are the main global trends, physical mechanisms that regulate star formation. And this could be, of course, feedback from black holes that tend to suppress star formation. Galaxies also interact between them, so they can trigger star formation and also suppress. There's also the impact of explosions of stars. So there are lots of physical mechanisms that happen there that we don't try at first order to understand in detail, but we try to see what are the main elements that regulate this star formation. And so this has been extremely efficient, and we have basically collected many of the, we know now globally, what are the main elements that regulate, or the main physical mechanisms that regulate star formation. We know that, as I said, there are mergers, there's feedback, which tends to regulate star formation, there's gas accretion, of course. So we have been, collecting different physical mechanisms. And so, and probably, so what's coming next is, trying to establish causal connections, trying to see exactly what are the physical mechanisms that connect to each other. And so we are now moving past this era of statistics, and in which I will try to talk today about how we are moving into a data-driven approach, or era, if you want to call it like that. So basically, what's happening now is that samples are becoming larger. So we are increasing the number of galaxies observed by several orders of magnitude with new facilities like Euclid, for example, that will be launched next year. LSST, that's also a ground-based observatory that will start operating within 2 years, more or less, and that will observe billions of galaxies. And also, data is becoming more complex because we are getting higher quality data. And so we have examples of, for example, resolved spectroscopy, in which we are not only taking one spectrum per galaxy, but we're trying to get at the same time imaging and spectroscopy. So this ends up with hundreds or thousands of spectra per object. And since also, instrumentation is becoming more powerful, we are going into more details. There's more information into the data that you need to extract. And the James Webb that will deliver data in the next few weeks is, of course, an example of this. So how do you handle this increase in magnitude, increase in complexity? And I think the answer for the community is quite obvious. And you can see it in this plot, in which I'm plotting here, just taking some keywords of in AstroPH, so published only in astrophysics as a function of time. So names, different keywords in the abstract of the papers. And I want you to focus on this red one, which is a neural, which refers to neural networks. And you can see how, since basically mid 2010, 2013, 14, you see an exponential growth of the number of papers using neural networks in astrophysics. And you can compare this with other fields, like, for example, galaxy formation, and you see that the relative frequency is flat. So there's no increase of papers talking about galaxies. There's an increase about Bayesian statistic, but this is unprecedented in terms of the exponential growth. And this is what is actually what I call the deep learning revolution. So basically, this is 2012 is basically when the first deep learning paper was published, not in astrophysics, and it took 3 years or 2 years to reach the community, and you see this exponential growth. So the answer to the community, to this data deluge that we are experiencing, has been turning to a data-driven approach or using neural networks to address this issue. So what I want to address today is, so it's been now a decade that deep learning is in the market and actively used in many fields. I would say that it's basically 6 years that has been used in astrophysics. So what I'll try to describe today is how it can be used is, something that will be used just as an incremental science. To do incremental science, we're increasing the number of objects, and we're just using this to do the same science we were doing, but more efficiently. Or it is something that will open a new way of looking or constraining the physics, in that particular case of galaxy formation. So this is an effort, and I will that we have been. It is part of our review work that we have done with my colleague François Lanus in France, and we have reviewed extensively all this amount of papers working on deep learning. I'm not trying to talk about this review will be out very soon, but we're not trying to describe precisely all this review work. I will focus today on the work of my group, but following the lines of this review. And so basically what we have been establishing here by doing this survey work of deep learning is what are the typical applications of deep learning, especially for extragalactic astronomy and cosmology. And so we have divided these into seven categories. I'm not entering into detail, but basically you go from things that will be more close to incremental science, in which you have deep learning used for low-level data processing, also for establishing some galaxy properties. So it would be doing things that we know how to do them, but we do them faster, let's say, and things that are potentially new. So finding new correlations in the data or new discoveries, which is ultimately what we want to do, which would be the new ones. So I don't have the time to describe all these categories. I especially will skip over things that are cosmology, because I will especially focus on galaxy formation today. But I encourage you to go to this review and look at it. And as I said, I'm not reviewing everything in the literature. I will focus on these different categories on work which has been done by my group and is currently being done, but it's of course not exclusive. So there's lots of people working on these. So let's start very quickly with deep learning for low level data processing, which is quite standard. And this includes several basic things that you can do with deep learning when you deal with these big surveys. Again, I will go quite quick, but basically I think that there's here a major breakthrough of deep learning in the community, which is basically, I would argue that it has solved the classification problem. So when you have, and this is what happens also so deep learning was essentially became popular in the computer vision community because it very efficiently can classify classes of objects. And so when you are faced and this is something that happens very often in science, is also in astrophysics. And one example is, of course, the Hubble sequence. So you have galaxies that come in different shapes. You have galaxies which are elliptical, galaxies which are spiral. And we know that they are formed differently because their shapes are different. And so sometimes when you get these huge amounts of data, you want to classify them in different boxes to analyze their properties and see how they form differently. So this has been traditionally done by eye. Then people have been trying to do measuring properties of these galaxies that correlate with morphology. But it turned out, and it's also it's always been a problem of doing this accurately and never as accurate as the human brain. Now, this has been essentially solved with deep learning. This is an example now, an old paper now, so since the beginning of deep learning, but you can see that the agreement that you get between visual classifications and deep learning-based classification is extremely high. And so just to put it in context of this breakthrough, this is what happened before deep learning, in which you see that you typically got 25 or 20, between 20 and 10% error. You go from 20% error to basically 1% error as compared to human classification. So this is a huge increase. So it's rare to see this improvement in science. And so basically what's happening, and this is something that is important, is that we change the way we address the data processing. That's why I'm talking about a data-driven approach. when you do, let's say, before deep learning, what people used to do is you take images of galaxies, you measure some properties that we call in machine learning features that correlate with the morphology. You would measure, like, you know, the symmetry of the light or moments of light that correlate, and then you try to plot these parameters in some kind of planes and see if, you know, different types of galaxies occupy different regions of the plane. Now, the problem that's all, and this is common to all machine learning, pre-deep learning machine learning approaches, in which basically you try to extract features. And the problem is the features don't properly, you know, or you miss some information in the extraction of the features, then you are lost. And so what deep learning does, it's replacing this feature extraction by some, in that particular case, convolutional neural networks. And so you remove all these feature extraction process, and these actually, you know, by optimizing end-to-end, you increase accuracy in a significant way. Okay, and so I'm not entering into details. I want to go into more exciting things. But I think for now, this is one of the major breakthroughs. And I'm talking here about galaxy morphology, but every classification problem that you can face with galaxy surveys, I think, is now accepted by the community that it will be addressed with deep learning in many cases. There are, of course, some issues to be solved. You have problems of training sets. You have problems of changing between different data sets. But, you know, the gain in accuracy that you get and in speed is just significant enough so that I think this is the basic approach that will be used in the future. And so I will like to focus, because of the limited amount of time, in, you know, what I think is, you know, beyond out-of-the-box applications of deep learning, so more specific to our field of galaxy formation. And so basically you can do classification, you can do segmentation, and this is basically doing what people do in computer vision and just extrapolate to astronomy. But now you can be more specific and try to use these neural networks, which at the end are universal approximators, to extract or adapt it to your field of research. And I want to focus here, for example, on how you would use this to extract galaxy properties. And there are many things that you can do. And now it's becoming more domain specific. You can measure distances of galaxies, you can measure stellar populations, you can measure galaxy structures, you can model strong lenses. So basically, and I think this illustrates how, again, this data-driven switch, in the sense that these are all things that we know how to do and that we have been doing in let's say, statistical data sets. We know how to measure photometric redshifts, we know how to measure stellar populations, properties, and we do it with specific software that we have developed over the years. Now, what's changing in this new approach is that all these, you know, are being replaced by, or can be replaced, let's say, by neural networks general neural networks that deal with this in a fully data-driven approach. And the advantages, again, are speed and the fact that you don't need to develop specific tools. And so you can then, as I say, infer different properties. And so basically, the standard way of doing this in the statistical era, let's say, is, as I said, again, you see the same process in which you get some data, which can be multi-wavelength images or spectra. You get some statistics, you reduce this to some statistics, and then you apply some specific software to get, you know, distances of galaxies, star formation rates, stellar masses of galaxies, or sizes or structural properties of galaxies. And for these, there are specific softwares. Now, when you do these kind of approaches, and over the time, people have been trying in these past 6 years, way of, you know, doing this more efficiently. And so we replace all these specific algorithms by neural networks. The advantage here is, or the motivation at least, not the advantage, I would say the motivation for doing this is, again, you need speed because you're dealing with billions of objects. So increasing objects by 2 orders of magnitude is not nothing, it's a lot. So you need speed, and these are extremely efficient. And so another advantage is this is algorithm free, so it's not algorithm centric anymore, it's data driven, essentially. This is a general framework, optimization framework. And so then you don't care, you don't need to specify a specific algorithm, and you don't rely on summary statistics. So basically you are using all the information that is in the data. So in that particular types of application, I would say that neural networks are used as universal approximators for accelerating and also hopefully to improve precision. So again, I don't have time to review everything. I'm just trying to focus, give you an example of this kind of approach of preliminary work. I prefer to focus on preliminary work that we are exploring and that other groups are exploring. One particular example that we try to do when we start to reconstruct or try to understand, as I said at the beginning, we try to understand how galaxies transform gas into stars, what the star form, and this is called the star formation history. So you want to understand for a given galaxy, if you go back in time, how it was this activity of star formation. There will be activity times in galaxies, lifetime, let's say, that it forms a lot of stars, others that it's more quiet. And this is translated into the star formation history that I'm showing here. This is cosmic time. So this would be, let's say, beginning of the universe. And this is today. And these are several galaxies from a cosmological simulation. So of course, you cannot get it from observation. These are cosmological simulations. But basically what you plot is the star formation rate. So it suddenly goes up and then it goes down as a function of time. So it forms a lot of stars down. It doesn't form stars. And you see that this, of course, you cannot observe it, because what you observe is a galaxy at the end here. Okay, you have one snapshot of a galaxy, or if you go at higher redshift, you might observe one time a galaxy, but you cannot follow it in time. What you observe from the galaxy is an imprint of the light emitted by the stars now. What are the stars of the galaxy at the moment of observation? And this is the light of stars for different galaxies as a function of wavelength. So, and this is what we call a spectral energy distribution of a galaxy, or a low resolution spectrum. And so basically what you're trying to, it is an inversion problem in which basically you try to get, based on the stellar populations today, or on the light emitted by stars today, a galaxy of observation, you try to get its star formation history. Okay, so this is more or less, we can do it in forward modeling. The traditional way would be, you generate some stellar population models because you know how stars evolve, and then you make some assumptions, you make them evolve, and then you fit, and then you get the star formation history that best fits your spectral energy distribution. Now you can do this, and this is the purpose of this, with neural networks. And again, I was saying this because we have cosmological simulations. So this is an example of a cosmological simulation in which you make galaxies evolve. And so basically what you can do in a cosmological simulation is precisely this. So taking a galaxy at a given time and follow its star formation across time. And you can also measure or perform mock photometry on these particular snapshots of a given cosmological simulation and produce the light emitted by stars. So you might want to use now a universal approximator, which is a neural network, to do this inversion problem for you, trying to get what's given a spectral energy distribution, what will be the star formation history, now learned from a cosmological simulation. And hopefully, if this is an observable, you can then apply it to observations. And so basically the approach that we follow here, and this is again another sign of how deep learning has evolved. Now deep learning is can be seen, as a probabilistic modeling. So we are not now just estimating point estimates by, but we are estimating the probability distributions. So basically what we're going to use here, and not entering into details of the technique because I don't have time, but you can use a deep generative model that basically is fed with a star formation history from a simulation and the corresponding SCD. And so basically what the deep learning model lets to do is it outputs a probability, this conditional probability function of SFH given an SCD. So star formation history given an SCD. So this is the conditioning. And so basically it learns to generate new star formation histories from the prior of the cosmological simulation, but conditioned to an SCD. So then when you want to generate a new star formation history, once it's trained, you tell the neural network model, okay, this is my SCD, generate all possible compatible star formation histories. And this is an example of what you get. For example, this is, again, this is very preliminary, but this is a true star formation history in blue from a cosmological simulation from one galaxy. And then what you get from this model is all possible all possible star formation histories which could be compatible with that particular SCD. And so these are the orange realizations. So you can sample from this probability distribution and have, which is a posterior distribution, and get compatible star formation history. So you see there's scatter because this is a degenerate link. But since you're learning the prior from the cosmological simulation, the overall mean posterior, sort of matches what you expect from the true SFH. And this is a way of and so basically what you're doing here is variational inference, but we are doing it in an extremely efficient way by implicitly learning the prior from the cosmological simulation. And so I will move forward because of the sake of time, but as I said, in that particular regime here, this is just an example of how you can accelerate stuff. You can also do photometric redshifts and in the same type of approach. But again, what I was saying here, and so there's a different subtle difference between B and D. Let's say here in B, what I was saying is that we try to emulate things that we know how to do. We can improve them, but ideally we know how to do them. Okay. In that particular D, what we're trying to use is the fact that neural networks seen or deep learning is not only a way of approximating universal approximation, but it also is a way of extracting features from the data. So I was saying you bypass the summary statistic steps. So basically you might ask these deep neural networks if there is some information in the data that you might have missed that can be used. And so there's more information that you are actually used to extract. And this is what we call, finding hidden correlations. And this is where I think it becomes also exciting. And that's why, it's potentially new in the sense that you might find new information in the data that you were missing. And that's another motivation to move for a data-driven approach. And so here again, I'm just focusing on giving you glances of things done by my group, but there's lots of people working on these. You can try to extract physical process of galaxy formation, which I will try to talk about this today. But you can also measure dark matter properties, which are typically not observables, but by going again to simulations, you can measure the properties of dark matter or extract relations between observables and dark matter, and so on. And so again, the idea is simple here. Essentially, you have some observables and you have some physical processes or things that are unobservable, which typically will come from simulations because you have no choice. And this is again a drawback, a problem of this, but I will emphasize the problems afterwards. But basically, the motivation here is that you want to improve or use neural networks as a way to improve the link between physics and observables, which is basically what we try to do when we do astrophysics, right? We have some observables and we want to go back, what are these observables telling us about physics? And so this link is usually degenerate, okay? And so you want to use maybe neural networks to learn implicit or complex nonlinear relations from simulations and try to get a better link between observables and physical process. And so again, this relies on simulations. And so, as I said, I've just described how we can, go back to the star formation history of the galaxies. But galaxies, they grow two ways. They grow because they form stars, because they have gas and they form stars. But they also grow because they accrete other galaxies. So you can have the stars that are created in a galaxy that you see in a galaxy at a given time of observations can come between, they are formed in situ, they are formed by that particular halo because gas is transformed, but they can also be stars that are brought by another galaxy which were formed in situ in another halo. These two halos merge, and then you increase the amount of stars. And so if you want to reconstruct, the whole formation history of a galaxy, you need to have both. You need to have the in situ formation and also the ex situ formation, so the stars that have been accreted, which come through mergers. And so, what as I told you, the in situ star formation gives some imprint on the SED of the galaxy, let's say. Accretion could also give some imprint on the stellar structure or the kinematics of the galaxy, because when stars are accreted, because when there's a merger of galaxies, this disturbs the movements or the motions of stars, and it creates some particular features in the data. Like, if you go very deep, you will see like remnants of mergers. Like, for example, there's a galaxy observed at very low surface brightness, and you see there are shells or signs of past interactions of this particular galaxy. But again, the link, so you want to say, given the observed kinematics and morphology of a galaxy now, how much mass has been accreted at that particular galaxy. And you see that it starts to be a complex inversion problem, because the link between these shell structures and the fraction of mass, or just the kinematics, is not straightforward at all. And so basically what you can try to ask is there some information on some observables on the fraction of mass that has been accreted. And for example, I'm showing an example of what I was telling you at the beginning about IFU survey. So this is part of the MANGA survey, in which basically you take a spectra for every region on the galaxy, a spectrum. And so basically from these, you can get resolved maps of properties of the galaxy, of the motions of stars, like the rotation of stars that you can see here. So things are rotating. Red means they go far from us, and blue they coming towards us. You have the velocity dispersion, but also metallicity and ages of stellar populations. And so you can ask the question whether these observables have some information about what's the past accretion history of a galaxy. And so again, if you want to do this in a classical, not data-driven approach, you will try to think about what you can measure or how this relates, or the structural properties relate to the accretion of mass. But you can replace this again by a neural network and say, let me know if there's some information. Maybe there is not. And again, trained on or informed by numerical simulation, the answer is yes. So basically, if you feed this by mock observables from a cosmological simulation, and again, these are probabilistic modeling in which you get error bars. And so basically what you can see is that I'm showing here the true fraction of mass, of stellar mass, that has been accreted by the galaxy, that from the simulation, because you can follow the merger history, and what you predict by using these observables. And you can see that basically, so 0 means this galaxy has all its stars from in situ. 1 means that this galaxy has everything from ex situ, so it's a huge merger. But you can see that there's a nice correlation between the true values and what you predict with a neural network based on these observables over here. So again, this is an illustration of how things that are not obvious to extract from the data, you can use a data-driven approach to try to extract this information. Now, the price to pay here is that you don't know what you're measuring, okay? So this is a big problem of this, and I will try to highlight this a little bit. Before I go to the problems, I will also illustrate another case in which now, falls into the same category. We are trying to understand or constrain the physical processes that, or the evolutionary pathways of galaxies across time. And so this is an example, maybe a bit more complex, but basically it illustrates how you can try to, informed by simulations, try to find evidences of physical processes, of reconstruct again the assembly history of galaxies. So this is an example from a cosmological simulation, again, in which you can see, again, as a function of cosmic time, the evolution for a given galaxy, a given halo of several properties. And you can see, I would like you to focus on the cold gas, which is measuring the reservoir of gas in the central parts of the galaxy. And you see that for that particular galaxy, you see that at some point, the gas density, the mass in the central part of the galaxy increases a lot. And this, because it increases a lot, it increases the stars, which is the red in the center. And then, once you formed a lot of stars in the center, the gas is depleted. But what's happening here is that we have formed a core. So you're basically building a bulge. So you're changing the morphology of your galaxy by an inflow of gas that creates lots of stars in the center. You create, an overdensity of stars. The galaxy becomes baryon dominated. You have more baryons, normal matter, than that matter in the center. And so basically it's a mechanism in which you transform the morphology of a galaxy. And so you want to find, and so again, what happens here is, and so this is a physical mechanism that is proposed by numerical simulations. And you can try to use machine learning or deep learning again to find evidences of this physical process. And so you can essentially transform these into, in that particular case, a classification problem. So you can transform in which basically you say, okay, galaxies go through different phases of evolution. This is a major assumption that you do, assuming that, first you are not, you are dark matter dominated, you don't have a core. Then you have the core construction, the bulge, build up, and then you have the post-bulge growth, in which the gas is depleted in the center, and basically the density in the core of the galaxy remains constant. And so you can, again, in simulations, you can follow an individual galaxy over time. In observations, you can't, but you can, go to observed snapshots of galaxies by the Hubble Space Telescope, for example, and then ask a neural network to tell you if these particular galaxies fall in any of these categories, and you can find galaxies in the different phases of evolution, for example. So it's another way of trying to reconstruct the past history. So in that particular case, extremely simple. You follow more or less a similar approach. You have a cosmological simulation. You create mock images in that particular case. Because you have the individual the histories, assembly histories of every galaxy, you can label them based on the physical processes on different categories. And then you don't care about what are the summary statistics that you're going to extract. You just ask a neural network whether there's some information here that you can extract. And again, the answer is sort of yes. I'm not entering into details, but this is an example of this process illustrated in images, in which you see image from a cosmological simulation of galaxies in the different phases. You see this, low density galaxy, then it goes this compaction event where you have this inflow of gas, it creates a core, and then the core is created and you accrete gas. Okay, and so this is a mock image from the high resolution simulation. Then you transform these as if it would have been observed by HST, by the Hubble Space Telescope, and then you ask the neural network and you find similar objects like that, and these are the real observations. Okay, so you can try to put galaxies in boxes, but now not based on just an apparent morphology, but on a physical process, for example. I think I had another example of these, of constraining formation mechanism, but for the sake of time, I think I'm going to skip that. I'm happy to go back to these about the migration of clamps and supernova feedback. I'd rather move to, let's say, some caveats maybe now, just about what I've just described. So you can, use, as I said, neural networks are extremely powerful to extract information from the data. But one particular problem that they have, or two main problems that they have, is that because you are bypassing on summary statistics, especially when you use deep learning, you don't have control of what your neural network is measuring. So we can use all information that is in the data. And so it's very difficult to interpret. And also, you are using, by training on a particular data set, what you're estimating a posterior, but it's a posterior under the prior, that it's implicitly learned by the cosmological simulation. And we know that simulations, for example, I'm talking about simulations specifically, are not perfect, because otherwise, there's no point in trying to learn anything about the universe if we know that we are already good. And so, because simulations made some assumptions, especially, I told at the beginning about, these large and small scales. You cannot simulate everything together, so you need to make some assumptions about the small scales, or the physics of the small scales. And so, which is called subgrid, and different simulations use different subgrid models, and so different assumptions. And so basically, if you learn an implicit prior from a given simulation, it doesn't mean that it's a true prior, and you might be biasing your conclusions towards the prior that you have learned. This is an illustration of these, for example, in which now, I showed you how we train on a given cosmological simulation, and it worked nice for recovering star formation histories. Now you say, okay, I'm going to test the same learned neural network now in another cosmological simulation with another subgrid model. And you see it's not that good here. So you see that, this is a true star formation history. This is a galaxy that had a very big burst of star formation at the beginning of its history. And you see that, because the posterior you estimate is a bit far. So you estimate some, samples get that there's something over here, but it's a bit shifted. It is not that accurate. So it probably means that there's some prior information that you're learning, or these types of star formation histories are not properly reproduced by a given simulation. And so these are one of the dangers. So you cannot apply this blindly. And again, another example, same exercise here for the accretion histories, train on one simulation, test on another. You see that here it works better. It's a bit overestimated over here, but this is, generalizing, I would say, more or less okay. And I think this makes sense because, you are essentially tracing figures of gravitational interaction, which, should be more universal. It doesn't depend that much on the subgrid physics, while here is about star formation. which is more related to feedback and how you model the small grain physics. Okay, so just two main problems, and I think that need to be worked, just to summary. So it's interpretability and the robustness. And we need to be very aware that when you train these, you are learning an implicit prior is extremely powerful, but it introduces some biases. So I will end the last few minutes so that about what we call the F category, let's say, which is how to use deep learning for discovery, which ultimately is what you want to do, is want to discover new types of objects. So these huge data sets that we will have are, have large quantities of objects, which means that potentially we can find new types of objects, but also new physics, and so, but you cannot do this manually. So how you can use or take the help of these data-driven approaches for discovery. And so this means that we are moving now into the realm of what we call unsupervised deep learning. So now you're trying to data mine your data sets. You're trying to not, extract or some physical property that you're looking for, but you're trying more to find what's in your data set. And this is what we call unsupervised. And ideally, so this is basically has been used for visualizing complex data sets. I told at the beginning, the data sets are becoming high dimensional, complex. So you have lots of objects, so you want to visualize them. But I think interesting to find outliers over here. And ultimately, there are some works now trying to directly extract some physical laws from the observation. So you get the data and then tell me what's the physical law that better explains that particular data. We are not there yet, but with some toy models, it has been done. So in that particular case, so basically there's no supervisor here. So basically the motivation here is you have a complex high dimensional data set and you feed these into a sort of neural network. And you ask typical questions like, what are the main patterns that I see on my data? Are there any strange objects? And so can these main patterns be explained by simple laws? And so again, the motivation here is that, as I was saying, future large data sets are impossible to data mine by eye in a reasonable time scale. And so basically what you want to do is help in finding patterns. And so here they are used as efficient probability density estimators. I don't have much time over these, but just show you a couple of examples, if I may. I don't know. So again, I'm going back to Manga, which is an example of high dimensional data set in which, again, I have hundreds of thousands of spectra per galaxy. And from these, you can build these sort of maps. But you see there's multidimensional information. You have rotation, you have gradients of metallicity, of age. And so instead of reducing the galaxy to a given point, you have a galaxy, it's becoming, you have resolving the structure. So you have way more of information that, extracting patterns from this higher dimensional data set might be more complex. So it's a good study case to see how machine learning can help into visualizing this data set. So you might say, I don't need anything complex. I can reduce this, for example, with principal component analysis. So I can just take these high dimensional data set, use a principal component analysis, and then explore what's in the data. If you do this, for example, in Manga, this doesn't work because Manga has a very complex observational scheme in which some galaxies are covered with small fibers, with few fibers. Others have lots of spectra. And so basically, when you do a simple PCA, what you encode is the number of fibers. Essentially, this is what the PCA is picking up. So some galaxies have more fibers than others, more spectra than others. And what you can see here is the color code is the number of fibers. And you see that you're grouping galaxies for non-physical quantities, which is something that you don't want. And so this motivates the use of more complex problems. And I want to illustrate these because this, again, I think is one of the things that it's now becoming extremely popular in the machine learning community. And I think, it's coming slowly to astrophysics, but I think it's extremely powerful. And which what we call self-supervised learning or contrastive learning in that particular case. And essentially what you're trying to do here is finding some representations of your data, you're reducing the dimensionality of your data, but you're using it by making the data a representation be agnostic to some particular augmentations or some particular perturbation of your data that you want the data to be agnostic to. So in computer vision, what you do is essentially you take an image, for example, you apply some particular perturbations, and then you encode these with different neural networks. And so, and you do this for a particular image, and lots of images or all the images in your data set. Essentially, what you want is that the final representations that you get from the image, if they come from the same image, but different views of the same image, they will try to cluster them together. Okay, you like that what you learn from these two branches, which come from the same image, are similar. But what you learn from different branches are dissimilar, very different. And so the advantage of this is that you are sort of plugging in what, you know, the augmentations you want your model to be independent of. And so in that particular case of manga, we want the model to learn something that is independent of the fiber coverage, for example, because, you know, we don't want non-physical properties to be. And so basically what you can do is take some manga maps and apply some perturbations, in particular resizing the number of fibers, applying some noise, rotating it so that it learns something that it's independent, and forcing this representation learning to be physically driven and not non-physical or instrumental driven. And actually, it turns out that it works. For example, this is a comparison of the PCA, and you see it's color coded by the fibers. But when you do this augmentation, then it's way more mixed. So the fiber information is not something that it becomes relevant anymore. And however, you start being sensitive to physical properties. Well, you see here that now I'm coding here by the velocity dispersion of the galaxy, and you see that you see a nice ordering of galaxies as a function of their velocity dispersion, while you don't see it in PCA at all. So you are forcing the representations to be sensitive to physical properties. And now you can explore these maps and see what are the main trends. And you can look at gradients of metallicities, gradients, and correlate how these different quantities correlate. So it's a nice way to explore the data. I don't have time, but you can apply also this kind of techniques for James Webb Space Telescope. This is something that we're doing with Luca here, but I don't have time to enter into details. But you can get basically the same idea to make predictions of what will be the morphological distributions of high redshift galaxies, and which become independent of the noise properties. And so I'll skip over these. I think I won't have time either to describe how you can find outliers. But it's also extremely interesting that because, as I said at the beginning, you can use deep neural networks to estimate probability density functions, you can estimate the probability density function of your data by feeding lots of examples, and then ask what are the objects which have a very low probability of observation, given what you've learned from your model. And these will pop up things that are very strange or rare in your data set, which are potentially discoveries. This is an example of this technique with generative adversarial networks, GANs in that particular case, to find outliers in a particular imaging survey. And you see that you start seeing that, you know, weird detection effects are clustered in a particular region, and you also find more extended sources or more interesting sources. So this is a way of filtering out things that are very normal and giving you only access to things that make that potentially are interesting. Okay, so I think I'll stop here with some very final thoughts. And this is part of, again, the review we are ending. So I'd say that, you know, deep learning has now, you know, been extensively used in astronomy for different applications that I've tried to discover. These are techniques that have been used, and this is just to highlight that very quickly, so the deep learning community creates new techniques very rapidly. This is a field that evolves extremely fast, but these new techniques penetrate rapidly into other fields. And this is a translation that it's becoming very democratic to use machine learning, which has, you know, some advantages because you can test new techniques very quickly. Some disadvantages because it's so easy to test that, you know, all the caveats or some of the caveats that or dangers that you have are not properly understood. This is just very quickly an attempt to measure what's been the impact in terms of citations and in the community of using machine learning or deep learning in a particular case for different science cases that try to describe galaxy properties. And so basically I'm showing here the number of papers per year. So this is 10. And so the citations per paper per year, as compared, for example, to galaxies. So you see, if you look at deep learning or papers using deep learning, it's still way less than the impact of papers using galaxies. And again, the field or the application that is still more impactful is still very basic processing, so classification essentially. So everything that looks exciting that I'm trying to describe still has a limited impact. And the reason is, I think, some of the caveats I described. So it works very nice at first stage, but then when you try to think about how I'm going to apply this in real life, you are faced with several problems that are not easy to overcome yet. So the main problems, as I described, I say that I think marked in red here is, of course, interpretability. The fact that in many cases we are forced to train on simulations, and this entails some problems because you are changing the domain and you don't control what's happening, and so and create some problems of robustness. So these are the main issues that need to be addressed in order, I think, to really move from the proof of concept stage to the deployment stage. But again, this is a very young field that's it's entering now. So I think the most impactful applications are still at the low level out of the box application, and potentially novel applications are emerging, remain at the proof of concept because there are some intrinsic limitations. It doesn't mean that they won't be overcome yet, but it's part of the process. Thank you so much, and apologies for being late.
Thank you, Marc. So I'll take the first question before leaving to people. So my understanding is that there are 3 players in the game: simulation, observation, neural networks. Yes. So we are not there in any of them, but where you see more room of improvement in the next years?
Well, I think thank you for the question. So the main room for improvement, I think it's really in so all the game here is to link two imperfect data sets, because observations have their limitations, simulations have their own limitations. So I think the main improvement is in trying to learn something from these two imperfect data sets without being biased by things that are not physically driven. So my understanding is that by developing more advanced techniques or ways of with removing spurious information and learning the basic or things, extracting the things that are really robust, this is the main for me the main improvement, right?
Question here on Zoom.
Yes, can you hear me?
Yep.
So I have a question regarding what you just said about the image limitation. How does the problem of resolution and sensitivity and noise and stuff like that, is that easier to solve using deep learning, or meaning that the parameters that you extract or the classification will be more accurate, or the problem stays the same?
So if I understand properly, the question is, how do you deal with the limitations of the data, which I said, okay, there are two sides of limitations. So the limitations of the data, if we talk about limited spatial resolution, noise, etc., they are there. And so the process, specifically when you try to learn something or extract some information from the data, informed by simulations, what you want to do is introduce all these data properties in your training set. So you want to take your simulations and you add all the noise properties and you limit the resolution at what you can observe. And so it's an indirect way of preventing the neural network to learn something that it's not observable. So you learn only think patterns that are accessible at the noise and spatial resolution. So this doesn't mean that, so basically you are limiting the amount of information that you can extract because the properties of your data you have. So you might get, if you increase resolution, if you get better data, the links that you're going to extract or the information will be improved. And so this is, intrinsically plugged into the way you mock your simulations, I would say.
I see. Okay, thank you. There are a couple more questions on Zoom. So Patricia, please go ahead.
Hi, Marc. Thank you very much for the talk. I really enjoy it. You mentioned that, for example, in the case of the star formation histories, you are limited by the star formation histories of your training set, which are the simulations. My question is, would it not be possible to extract as an output like chunks of the star formation history, like a fraction of mass at different ages, and then being able to create a different star formation history with the same input, or not? I don't know if that.
Hello, hi Patricia. Let me see if I understand properly. You say instead of getting directly a full star formation history, you want to extract fraction of masses at different of stars.
Yeah, exactly. And instead of the output being the whole star formation history, so you are limited by the star formation histories you have, put as an output,
as a function of time.
Yeah.
Yeah, I see this even more complex because you have several dimensions then to extract. In theory, it's possible, I think. Do you think that this is more robust, so that at the end it will be more, or at least?
I think that you are limited. Sorry.
No.
Sorry.
You are motivated by interpretability. I'd say that it's easy to understand what you're measuring, essentially.
Yeah, I guess I was trying not to be limited by the star formation histories of the simulations, but to be able to create a new one if you want to put it like that. Like.
I see your point. Yeah. Okay. Yeah, that could be an option. The other option that we're trying to explore is trying to make things robust. So learn a prior from a cosmological simulation, but not stick to the prior. But it is, maybe by training with different simulations, or there are techniques to try to bypass this. But this is an interesting idea.
I have another question related with the, I don't know if related with the previous questions, because well, it was just a TFM that I made with a student, and he trained the network using errors, and I mean without with errors and without using errors. I mean the way that you said, taking the models and also introducing the limited resolution and noise, etc. And the results, when applied to the real data, I mean, we cannot say they are better because you don't know what the real data are, but the correlation with other properties, for example, the mean age or the mean metascity, were much better when he trained the network without the noise than when he did it with the noise. I mean,
yes, that makes a lot of sense. This is what I'm saying. So if you don't have any noise and you have the highest spatial resolution and everything, you are in the best case scenario. So you will get, of course, it makes all sense, the best correlation. But you are.
Yeah, but with the data, I mean, I'm saying we train the network with and without noise.
Yeah, I know. And then
the output,
data,
when we apply the real data, the result will be better in the network train without the noise.
Without the noise.
Yeah. Okay,
that's
weird, no?
That's weird. Yes, that's weird. Yeah. I mean, again, I think this is this is a problem when you work with neural networks. I was saying at the beginning. So it's you don't know what you are measuring. So, and it's a nonlinear estimator, and so you might end up with things like that you don't know how to explain. And this is part of the limitations that I was saying.
No. I mean, I was because of your experience, but I was wondering if it couldn't be that actually, the network learn better without the noise, and then deal with the data.
Yeah, you might be. Indeed, you might be in a situation in that you provide more information. It allows the network to converge better, but it's not learning anything that it's below the noise level, let's say. So it's able to generalize properly.
Okay, thank you. But I have more questions, but I'll try to limit later.
Okay, so there is one more question. So Pablo Perez González, please.
Hi, Marc.
Hola, Pablo.
I don't know if I have an accurate view of this world of machine learning and deep learning. So correct me if I'm wrong, but what I see is that there is an increasing community of I think they call themselves data scientists, producing a lot of algorithms and code and these deep learning techniques with a lot of filtering and all that. And you have said it, that it arrives to science and to astronomy at some time, and but we take what other people have developed. That's how I see it. What other people have developed for many different problems without physics inside, but with a lot of filtering, and then we take those black boxes and try to adapt to our problems. So I don't know if that's accurate. I want to hear from you. And if that's accurate, then is there room to make our own networks and our own algorithms and to tweak them or create new things that really help with the physical interpretation of the data, or everything is already done by those people that are not scientists per se, not astronomers? Well, there are some astronomers there, but they call themselves data scientists, but they are not applying physics
Yes, yeah, completely. You know, this is a very nice question, and I think this is one of the main things. So I was trying to say that for now, these methods penetrate very quickly. They are democratized in the sense that people have created a very easy way of using these. And most of the applications that are done are indeed out of the box. So we take a new method, we test it, we tweak it more or less so that it applies to our data, but there's no physical information. So we have moved for something that is, let's say, or you are moving from something that is purely algorithmic centric to something that is purely data driven. And probably the answer is in between. Is you want to have a data-driven approach for which things that you cannot explain, but by plugging in, as you say, most of the physics so that the interpretability remains controlled. So this requires way more work and way more knowledge of the community of how these things work. And so I think there's a difference between people applying things and people actually working on how things work. This community exists in astrophysics. It's much smaller, but there's lots of people working on trying to make neural network architectures that, for example, are aware of symmetries that are intrinsic on your data, or you plug in some physical information and then you use only the neural network for when you don't have any physical model. And this is called hybrid modeling. And it's part of, you know, it's I think one of the exciting avenues for the future. So we have passed this phase in which, wow, this is exciting. There's lots of new tools. Let's try to test them. Now we are faced with the problem of how to move from this proof of concept stage in which, I have this method. For now, the papers that we are seeing is, most of them, I would say, is I have this physical problem. I apply the neural network. It works fine on my toy example. But, you know, going beyond that and making a discovery and making a science paper, there are some, but they are basically, you know, based on classification. More physical and advanced issues, there are less. And so I think this requires a deeper understanding, and interpretability is one of the issues. And having, you know, this hybrid modeling and getting neural networks that are, let's say, applied in a surgery mode, in which basically you inform the model by all the physics that you know, because you know a lot of physics, and then use the data-driven approach for which you don't know. And this is, I think, one of the main developments for the future, I would say. But, you know, it requires, as I said, more understanding of these techniques. I don't know if that answered your question. Yes.
More questions?
Okay. There are no more questions on Zoom. Thank you very much, Marc, for such an interesting talk.
Thank you.
Thank you very much. So I just remind everybody that you can see Marc's review coming soon.
Yeah.
Yep. So thanks again to be with us, and thanks everybody. And we see you next seminar.
Thank you.